Hi everyone, welcome back. So as promised, we're going to do some indeterminate torsional member problems. Indeterminate torsional member problems. So in this one, we have a composite assembly consisting of a steel core connected by rigid plates at the ends to an aluminum tube on the outer edge. Aluminum tube is hollow, steel core is solid. You can see those dimensions right here. Now, what do I want you to find? Well, if the torque is 1100 newton meters and it's applied to that composite assembly, I want you to figure out the maximum shear stress in aluminum tube and the rotation angle of NB relative to end A. So if end A doesn't move, how much does NB move? Okay, with that in mind, go forth, try it out. Look at those steps from earlier. This is not an easy problem, but we've done ones that are similar to it with axial loads. So check it out, see how it goes. And then come back and we'll do it together. So 3, 2, 1, and let's continue. So the first thing we always tend to do is get those polar moment inertias calculated. So we have our aluminum tube right here, and we have our steel core. As you can see, the aluminum tube, huge polar moment inertia because of the large diameter, even if we're moving a lot of material. Then we run out our equilibrium equations. So what's the torque going to be? Well, the torque's going to be equal to torque 1 plus torque 2 times 1100 newton meters. And here's the issue. We can't solve that. That's not enough equations. We don't have enough information yet to be able to solve that. And so we have to get more equations. Well, where are those other equations going to come from? Well, luckily, we can find out something from the deformation. So since they are attached by rigid plates at both ends, then the angle of twist must be the same. So we can write our compatibility equation right there. Phi1 will have to be equal to Phi2. And I gave you that in the common cases. Now how about our torque-twist relationships? Well, we know what Phi1 and Phi2 are. We don't know what the torque 1 and torque 2 are, but we know the lengths. We know the polar moment of inertia. We know the shear modulus, which it seems like we just might be able to solve this. So here we go. We have a second equation now with two unknowns, torque 1 and torque 2. So we can then solve for our torques. And we get that torque 1 is going to be equal to 8.071 times torque 2. And then using our original equation, we can solve for the torque in the steel core, which comes out to be 121.254 newton meters. And the torque in the aluminum tube would then be 978.746 newton meters. Okay, so steps. We wrote down our equations. We realized we couldn't solve it because our equation of equilibrium didn't help us. We looked at the geometry to figure out how they're connected. We wrote down our torque twist equations. We turned it into a compatibility equation, and then we kept on moving until we solved this. So now we can figure out the maximum shear stress. Well, that's going to be in my aluminum tube, or at least actually shear stress in aluminum tube will be at the outer edge, which we have to make sure we convert to radius from diameter. And I'm using that handy little calculation where I know that 1 Newton per millimeter squared is equal to 1 megapascal. I know I say this like every single time, but I want to keep on saying it because it's extremely helpful and I don't want you to forget. So with all that multiplied together, I get that the shear stress, maximum shear stress in the aluminum tube is 67.5 megapascals. And for the steel core, it'll be 77.2 megapascals. 77.2 megapascals. So even though the torque in that aluminum tube was significantly larger, the shear stress is actually less. And that's simply because of the difference in the polar moment of inertia. Polar moment of inertia for the steel tube is much, much smaller, and therefore it's going to feel much more stress. Okay, now what about our rotation angle? Well, we know what the torques are. We know everything we need now to be able to calculate this rotation angle. And so rotation angle 1 is equal to rotation angle 2, so I can just use one of them. So I'm going to use it for aluminum. I plug in my torque, the length, I convert to millimeters, And I'll make sure that everything else is in the proper units. And what do I get? Well, I get it's going to turn by 0.0289 radians. 0.0289 radians. So that's it. Yep. So thank you for listening, and I'll see you all next time. Have a wonderful day. Bye.